It's recording. All right. So today I'm going over final exam review differential equations content. So weeks 9 through 13. My name is Ryan Joseph. I am a TA for Dr. Paterka's section. I TA'd this class last semester. And I really enjoy it. I'm a sophomore studying bioengineering, just to give a little context on myself. And so we'll be covering weeks 9 through 13. I am doing content review and basic questions that I'm examples. Dylan is in another breakout room and he is doing just general questions that you have, or if you have any specific examples you want worked out, feel free to go ask him any questions. And yeah, so I'm just going to get started. Okay. So general information about the final. It is this Thursday, May 4th from 9 a.m. to 10 a.m. based on your professor. You're either going to be in Stittler B6, GRL BA1, or Leidy 10. So just be there early. I tried to get there early, especially Leidy 10. That's in the biology building, which I know a lot of people aren't sure where that is. The final will be cumulative. Any content from 1.1 through 13.2 is fair game, except for the specific questions that are not going to be asked, which to note would be in week 8, we're not doing PCA with SVD, as well as in week 10. Week 10, lots of the content was removed. It's just Cauchy-Euler equations. There's no planetary motion, physics, etc. You're allowed to have one front and back handwritten sheet. Make this early. That's a lot of content to put on one piece of paper. You'll have 2 hours to take this exam. It's going to be a total of 6 to 8 questions. They didn't clarify on how many questions exactly it's going to be, so I'd be prepared for that many questions. Okay. Again, these are review sessions. If you have any questions, go ask Dylan. If you just want to listen to examples, you can come talk here. Okay, so these are the general topics that can be covered over differential equations. So week 9, we're doing first order and second order differential equations that are constant coefficient and non-constant coefficients for first order differential equations. We're also using the Wronskian to determine linear independence. Week 10, like I said, the only thing is going to be those Cauchy-Euler differential equations. Know how to solve those, and for everything for week 9 and week 10, be able to solve them if they're homogeneous or non-homogeneous. Week 11, it's all of those, the introduction to our systems of differential equations. So if we have x prime equals ax, can you solve for the solutions, for real solutions and complex solutions, because they look slightly different. And then if it's for equivalent first order systems, if you're given some second order differential equation, can you convert it to a first order system that you can then solve? Week 12, we now have non-diagonalizable systems. So we are utilizing the fact that x is equal to py, where p is the matrix of vectors when you do a Jordan form of a matrix that's non-diagonalizable, as well as the two other main topics are variation of parameters and the method of undetermined coefficients. Those are both used for non-homogeneous systems. For non-homogeneous equations, we use a different method of undetermined coefficients, what we've been doing in week 9 and week 10, which some of you guys know is the annihilator method. But this method is when you have a system that has an f term, like x prime equals ax plus f, and how you solve that. And finally, week 13, we're doing phase portraits and classifying critical points. So given a system, can you determine what that phase portrait looks like? This was done quiz pretty heavily on quiz 6 and the requiz. So having an idea of how to do that, that's something I'd put on a cheat sheet, what the eigenvalues tell you about the phase portrait and what it's going to look like. And then also using the Jacobian matrix to determine classify those critical points as stable and unstable. Okay, week 9. I have these slides that have that give like a flow chart on how to solve these equations. I'm going to put it in the chat because I know not everyone has access to my slides because not everyone is in Paterka's section. Okay. Sorry, 1 second. Oh, sorry. Where is, oh, there we go. Putting this in the chat. Okay. Back to this. So this basically explains how when we have a first order differential equation, it is going to be of the form y prime plus p of t y equals q of t. This is the standard form of a differential equation. If you're ever given a first order differential equation, the one thing you need to do before you solve it is isolate that y prime term, so get it by itself, and then that's how you can decide what type of equation you have here. So the first thing when you're solving first and second order differential equations, always isolate that y prime term. Homogeneous means that we're set equal to 0. Non-homogeneous means that we're set equal to a non-zero term. This can be constant or non-constant. First order differential equations are pretty straightforward. When they are constant coefficients, you kind of just do algebraic manipulation to get the y term by, you want to get the y's with the dy's and the dependent variable, so like t, or independent variable t or x by itself with its differentiator, so dx or dt. From there you can integrate, and then that just comes back to basic calculus. Make sure you include the plus c term. If it's an initial value problem, you'll be asked to solve for that constant. So here, this c and this c, and you can also assert that c is equal to e to the c. That's another thing. So being able to solve for this constant term given initial values is very important. The one main thing about first order differential equations that's kind of unique that you need to learn for this course is the integration factor, which is this mu of t, or another term, but it's essentially equal to e to the integral of pt times dt. The integral of p of t. This allows you to convert the equation. It essentially is reverse product rule, if that makes sense. So you multiply the entire equation by this factor. And again, when you're given this equation, you have to isolate y prime, so divide by anything that y prime is next to, so you get the correct p of t term. And then you're able to multiply by this e to the integral of p of t, and this always turns it into this. So if you look here, it turns it into the integration factor times y. It is always this, and it's the derivative of that. As you can see, this entire term becomes this, derivative of this, which then is very easy to take the integral of, and then you can solve. Same thing when it's non-constant. You just multiply the entire thing by this integration factor, take the integral, which over on this side, again, it's fundamental theorem of calculus, the integral and the derivative cancel out, giving you just the integration factor times y. And then you just take the integral of this side, and then that's your solution. Again, remember plus c, and it's really that straightforward for first order questions. And again, I'm going to go over examples of a lot of these. I'm just going over content right now. Second order differential equations. Also, I'm sorry, this quality sucks, but these are, I feel like, more fun in my opinion. So again, you have a standard form of a second order differential equation, which looks like y double prime plus p of t y prime plus q of ty is equal to f of t. You again can have a homogeneous or non-homogeneous equation. This again means if it's set equal to 0, if it's not set equal to 0. For these with non-constant coefficients, the only application we do for non-constant coefficients of second order differential equations are Cauchy-Euler equations. The only type of second order non-constant equation you will be asked to solve or potentially asked to solve are Cauchy-Euler equations. So don't bother worrying about, I guess if you're given a problem and you see that it's non-constants, like if p of t is not like a constant, if it's like a function or an x or a t, same thing with q of t, first of all, make sure you isolate y double prime. So after you divide by this term here, is it still all non-constants? If it is, it's going to be a Cauchy-Euler equation. You know that because that's the only thing covered in this class. So when there are constant coefficients, so such that P of t and Q of t are just numbers or like real values, the method we use is just finding the characteristic polynomial and solving it there. So again, this terrible quality, but if you recall, it's doing r squared plus ar plus b. You find that quadratic and you solve the quadratic. Based on those roots, that's what your solutions look like. This is really bad quality, but this is something I would really recommend having on a cheat sheet. So after you solve a differential equation and you're given a second order differential equation, you find the characteristic polynomial and you find the roots, you already know what your solution is going to look like. And you know that because it's always going to be one of these three. You're going to have real and distinct roots, complex and distinct roots, or real and repeated roots. We are allowed a cheat sheet on the final. You have one front and back cheat sheet. Sorry, I was reading chats. So again, have this on a cheat sheet so you don't have to worry about memorizing this. I think for this exam, the less you need to memorize, the better. So just knowing, given a problem and you have the resources to solve it, and having maybe even examples of problems. This is something I recommend is like, if you struggle with a certain type of problem, having an example of it written on your cheat sheet so you can look through it as you're doing it. So I would recommend that for SVD. I'm not doing linear algebra portion, but problems like that you want to have an example of, I would do that. Okay, so for second order differential equations, returning to the topic at hand, when they're non-homogeneous, we have to solve for our homogeneous solution and our particular solution. So again, this means our solution is equal, y is equal to yc plus yp. Solving for yc is the exact same. So we have our roots, we solve for them, it's of these forms. If you're given these constants, make sure you include those constants. If you're including initial values, you make sure you should be able to solve for them. Solving for the particular solution. So we make an educated guess and we use the method of undetermined coefficients. Other people use the annihilator method. I'm not as familiar and I don't use the annihilator method, but if that works for you, that's great. For the way that I've taught it and the way I've learned it is, given this f of t, you make a guess on what you think the solution is going to look like. So it's going to look similar to what you're given. So if it's some constant, it's going to be some at plus b. Again, having this chart, if you use the method of undetermined coefficients, is very useful. And then making sure that your particular solution doesn't overlap with your homogeneous solution is also very important. So after you solve for your yc, make sure you always solve for yc first. Then when you're going to take your guess, if your guess, so if this f of t term, this non-homogeneous term, has the same like function as your homogeneous solution, you can't allow that to happen. Like, and since the solution is a linear combination of the homogeneous solutions and the particular solutions, in order for that to be true, they have to be linearly independent. So you can't have yp have any overlapping terms with yc. And in order to ensure that, so for example, that would be if this term was c2e to the 3t and your f of t was like 5e to the 3t. If they overlap like that, your guess is now a t e to the 3t. So you multiply by any t necessary in order to make sure that there is no overlap between the homogeneous and the particular solution. Again, you solve for it, you solve for this coefficient, and then your entire solution is equal to the sum of the homogeneous and particular solutions, so yc plus yp. Okay. There we go. This is a list of all the types of questions I would expect to be asked relating to weeks 9 and 10. This is also in my, okay, also I did a video solving a bunch of differential equation problems, week 9 and week 10. I can put the link to that in the chat too. Yeah. So first order separable differential equations, first order non-separable, so we went over when they're homogeneous, non-homogeneous, when there's constant, non-constant. Second orders, when they're constant coefficients, we solve it using the characteristic polynomial. When they're non-constant, that means it's a Cauchy-Euler equation only. That's the only type of question you're going to be asked. So being able to solve that, which we'll go over in a second. Also, again, like I mentioned, be able to solve all of these as initial value problems. So if you're given initial values, can you solve for the constants associated with it? So for first order equations, there's going to be one constant. For second order equations, there's going to be two constants, C1 and C2. Be able to solve for all of those if necessary. Computing the Wronskian, we'll go over that. So the Wronskian is just a set of matrices of, it's a matrix that includes any functions that determine if they're linearly independent. If the determinant of this matrix is non-zero, they're linearly independent. If the determinant is always zero, it is linearly dependent. Okay. But, okay. My screen should be shared, right? Is my screen sharing right now? I believe so. Sorry. Let's figure stuff out. It's sharing? Okay. I think it was gone for a second, now it's back. Sorry. Sorry, 1 second. Okay, sorry. Back to content. So Wronskian, and then these are special types of questions that they could ask regarding second order differential equations in the Wronskian. So given one solution in the Wronskian, can you solve for the entire second order differential equation? And then similarly, given two solutions, can you solve for the second order differential equation as well? Solving from one solution, and if you're given one solution and the second order differential equation, can you solve for the other solution? So these are just the types of problems that I went over in my video, as well as I would expect to, like, these are very fair game for this content. Okay. Cauchy-Euler equations. So these are a specific type of non-constant second order differential equations. They have a specific form that you should be able to recognize, but again, like I said, you're not going to be asked anything that are non-constant that is not of this form. So you should be able to assume that if you're just told solve this, that it's Cauchy-Euler, but it's going to be of the form. So for us, it's only going to be second order. So this n is going to be 2. And then this term right here is the second derivative. So it's going to be like y double prime. It's going to be like constant x squared y double prime, constant x y prime, and then all the way down to constant x y. And that can be homogeneous or non-homogeneous as well. The way we solve this is we set it equal to, sorry, I don't have this on here, but y is equal to x to the p. That's the important thing to remember when we're solving these equations, is literally just y is equal to x to the p. And then, sorry, you solve it from there and you solve for p. So p is, again, it's going to be just a polynomial, just like we talked about with the characteristic polynomial. And we solve that to give you p, and then based on the roots that you get, this is your solution, what's going to look like. Again, this is very similar to second order different constant coefficient differential equations. This is something I would have on a cheat sheet and be ready to expect it to do, because it is just always going to be of these forms, knowing that you might be able to solve for these constants, but it's always going to look like this no matter what. So again, that's something on a cheat sheet that you don't have to worry about, that you can just do easily. Okay. Week 11. These are our diagonalizable systems. So we're introducing systems of differential equations. For week 11, they're diagonalizable. So x prime is equal to ax. These will result in, the method for solving diagonalizable systems is given A, which is probably going to be a 2 by 2 matrix. Sometimes it's a 3 by 3 matrix. We diagonalize the system and find the eigenvalues and the eigenvectors. That's the main idea. Once we solve for the eigenvalues and the eigenvectors, if the eigenvalues are real, they look like, it's going to look like this. But if they're complex, it's going to look like this. I'll do an example of both. But you should be able to form, it's always going to be, again, cheat sheet content, cheat sheet after cheat sheet content. I would put this on a cheat sheet based on, this is what your solution, if it's real, it's always going to look like. It's going to be a constant times the exponential to the first eigenvalue times t times its respective eigenvector, and then same thing for the second set. For complex ones, this is the generalized eigenvector, and then this is of the form, your eigenvalues of the form lambda is equal a plus ib, which then looks like this, and then you just solve it from there. So good cheat sheet content. The other content from week 11 is equivalent first order systems. So what if there's only, sorry, I don't have time to answer direct messages, so I'm going to answer them as I see them. What if there's only one real solution? So the only way that there'd be one real solution would be that it's a repeated eigenvalue, and that's totally valid, but it's still going to be, you're going to have two, you will have the same eigenvector. So again, for A, when it's diagonalizable, if it's lambda is equal to, if it's equal to 3 or something, you'll have the same eigenvector. That should be, if it's repeated root for a system, it's going to be non-diagonalizable. Actually, it can be diagonalizable. Yeah, it's going to look like this, but another term, you'll have to have two terms because again, there are two solutions. There's not just one solution, even if it appears that there's only one eigenvalue, but it would have that t term to make them linearly dependent. So similar to, similar to, this is really bad quality, I'm so sorry. When they have repeated roots that are real, you multiply the second term by t to make them not linearly independent. To make them linearly independent, not linearly dependent. So same thing here. If they're the same, and they were diagonalizable, I would just multiply this by t, but it would still be the same lambdas and the same eigenvectors. That makes sense. Okay, equivalent first order systems. Given one or more second order differential equations, can you make it into a system? This was tested on one of the quizzes, and I saw a lot of people were confused about this. So making sure if you're given, if you're given a system, can you turn it, if you're given a differential equation, can you turn it into a system that you can then solve? That was on, I believe, week 6, the quiz 6. But yeah, this is the main thing here, is that you set one of the terms to its derivative of the first term, and then you make it into a matrix and solve it like that. Week 12, this is a very large week of content that is kind of confusing. So if there's 1 week from differential equations I would focus on, if it was me, it'd be this one. So these are when we have non-diagonalizable matrices. We find the joint canonical form, and we use that to make our general solution. And again, like I mentioned earlier, it's not just, you can't just solve for x that way. You have to solve for y, and then you find x from there, which we'll do an example of. And also fundamental solution matrices. This is could be asked, but it's basically the matrix of the solutions such that if you plug in 0, it forms the identity matrix, which is something that could be asked, like on an exam, it'll be like either form fundamental solution matrix or find the matrix such that f of 0 is equal to I. So I would know that the fundamental solutions matrix holds this practice. Should we practice going from a system to a differential equation? Yes, we should be able to do a system to a, given a first order system, can you form a second order differential equation from it? There was a question on one of the quizzes about that, I believe. Let me see. I'll find it in a second. That was me answering a chat question. Okay. Non-homogeneous systems, that is the other component of week 12, which is given it's not x prime is equal to ax anymore, it's x prime is equal to ax plus f. And what we do with that f term, like we mentioned earlier, the entire solution set is the sum of the complementary solution and the particular solution. Even when we have systems, we have to solve for the homogeneous component and then the particular solution, add them together, and that forms our final solution. We can use two different methods for non-homogeneous systems. We can either use variation of parameters, or we can use method of undetermined coefficients. So variation of parameters is the method with the integral that hopefully you guys remember. I'll show it in a minute, but that is more, I guess, more generic, if that makes sense. So you can always use the variation of parameters to solve a differential equation's particular solution. But for method of undetermined coefficients, you have to make sure that this f term and your complementary solution don't overlap, like I mentioned. So when you have given your solution and then given your f term, if they overlap, variation of parameters is going to be a better bet. But if they don't overlap, you can use undetermined coefficients. We'll show that in a second. Okay, last week, week 13. So week 13. Autonomous systems are basically week 13 is the geometry of these systems. What does it look like when we graph it? And again, when we graph it, those phase portraits that we draw, so you do the critical points and then you draw, like given the critical points, you know what it's going to look like. It's going to be a node, it's going to be a saddle point, it's going to be a spiral, all of these things. That is determined by the type of solution. And then every trajectory that you draw is a different solution to the system based on the initial conditions. So we're talking about those constant terms. Given those constants, C1 and C2, those determine which trajectory it's going to look like. So I just like those phase portraits that you're drawing are the infinitely many trajectories that exist, or the solutions that exist based on what those constants are. Okay. Autonomous systems are systems that don't have any explicit dependence on t. So if it's just like x prime is equal to 3x, that doesn't have any dependence on an independent variable, just the dependent variable, if that makes sense. And then the last thing are the Jacobian matrices, which we use the Jacobian and the Wronskian. Don't confuse those on the final now that we have two similar matrices, but they're still different. So the Jacobian is a matrix of partial derivatives that you use to determine the type of critical point of that you're given. So you would solve for the systems, you'd solve for the critical points, plug that in, and then from what the Jacobian says, that is what your system is going to look like. That's what your everything's going to look like. This was from Professor Perot's worksheets, week 13 worksheet, which I thought was a good summary, which would be a good thing to have on a cheat sheet based on what, given your diagonalizable system, what do all of these look like? So if it's diagonalizable with real eigenvalues, if they're both non-zero, the same sign, if they're equal, it's like this. If it's positive, it's a source. If it's negative, it's a sink. Same thing here. Eigenvalues are non-zero of opposite signs, so the saddle point. So positive eigenvalue, negative eigenvalue. One is 0, one is non-zero. There are portions of straight lines. Complex eigenvalues, we're going to have our spirals. So it's either going to be, if the real part is positive, I believe it's a source. If it's negative, it's a sink. If it's just pure, it's just going to be a concentric circles. Non-diagonalizable with a real eigenvalue. The eigenvalue is non-zero. It's I believe it's an improper source or sink. And then the eigenvalue is 0, parallel lines. Okay. So that is all of the content for differential equations, kind of like a crash course on, I kind of went over what you should put on a cheat sheet. I would honestly write down everything you want to put on your cheat sheet and then go back and add things. Like go through each week and then decide which you want to add to all of them. Again, it's a lot of content on one 8.5 by 11 piece of paper, so I would make sure to plan it out. You're probably going to have multiple drafts. But yeah, okay. Now I'm going to do questions. Yes, there's no PCA on the final. That is confirmed by the professors. PCA, yeah, so just SVD. I would know SVD. This is probably going to be gone over in the review session tomorrow by Nybris and whoever else is at that review session, is no PCA and no SVD to the extent that it was tested that one time on the exam. I don't remember exactly which quiz it was, but it was like, given this matrix, can you form this other matrix? It wasn't like do the entire singular value decomposition, it was doing parts of it. So I wouldn't expect to do an entire SVD, but knowing what each component of that, so like the sigma, the Q, and the P, what do those mean? But yeah. Okay, sorry. Least squares. I think, let me look. Sorry. Sorry. Least squares is not going to be on the exam. So, okay, I'm looking at what Professor Pritchard proposed. So Kepler's laws on planetary motion, and then resonance, transients, and modulation and damping. So all of week 10, except for Cauchy-Euler equations, there's not covered. So if you're doing practice problems and it goes over the physics of anything from that's related to springs or anything, ignore it. 14.1 for week 14, ignore that. 13.3 is springs with systems of equations, so that's not applicable either. Don't worry about that. And then again, yes, least squares, normal equations for least squares, regression is not on there, and then PCA is not on there. Okay. Sorry, 1 second. Okay. Content. Okay, so these questions, sorry. These questions come directly from the differential equations review session that I did before that quiz. So before quiz 5, I believe. That should be linked. It's linked in my week 9 slides that I sent in the chat. So the recitation material in week 9, there's a slide that goes over, it has my solution set, and it has a link to a YouTube video that's a recording of me going over every solution. So if you want to just review week 9 and 10 differential equations. These are all the questions I went over. I'll do a few right now, but if you want to see all of these examples worked out, that is a great resource, because I feel like there's so many different types of questions that could be asked related to differential equations, and it's like good to have like a comprehensive idea of all of them. So yeah, 1 second. Okay. 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 So this is the question I was talking about that is related to all of week 9 and 10. Just speed running through some of these, because again, the full video is linked in my week 9 slides. So this is a first order differential equation. It is separable, which means that we can separate the x in the dx terms and the y in the dy terms. So that's the best way to solve these. Don't try to use the methods that we discussed earlier to solve these, because it's kind of redundant or like not necessary. So I'm going to turn this y prime term into dy dx, because that is what it implicitly is equal to 3xy squared. We want to get the di's of the y's and the dx's of the dx's. So I'm going to just multiply each side by dx and then divide this side by y squared, which gives us this equal to 3x dx. From here, we can just take the integral, pretty straightforward, which then we know this side is -1 over y is equal to 3x squared over 2. And then remember doing that plus c. Don't forget the constant. And then the last thing we need to do is solve for y itself, which is just going to be y is equal to -1 over 3x squared over 2 plus c. Here we are given initial values. This makes this initial value problem. These are all initial value problems just to show examples of them. So here, if we're given this term, so we're given an x value and then what the corresponding y value is, can you solve for c? So I'm going to plug both of these into the equation that we just solved for. 1 squared over 2 plus c, which then has us -1, 3/2 plus c. 3/2 plus c is equal to -1/2. C is equal to -4 over 2, which is equal to -2. Then our general equation is going to be equal to the solution we found earlier, plus including that constant that we just solved for. So -1, 3x squared over 2 minus 2. That's our solution based on the initial values. I'll do this example. So this is a first order system. It is non-constant coefficients, as we can see. But the first thing that we need to do, given this equation, is turn it into its standard form. This is not its standard form because it has this term with the y prime. The only term next to your y prime should be 1. It should be by itself. So I'm going to divide by x squared for xy is equal to 1 over x squared. This is our standard form. Now we can start to solve this problem. If we recall that I was mentioning earlier, this is standard form u of t. So this is our p of t term. This is what's important because in order to solve this equation, we're going to use the integration factor method. Our integration factor is this mu of t. This is just what I call it. I think it's called in some places too. E to the integral of p of t dt, like we were discussing. I'm going to use this to help solve my problem. So in this case, d is going to be u of x equal to e to the integral of 1 over x dx. Again, I just found p of t, which in this case is 1 over x, plugged it in here, and then solved that. So this is actually e, the integral of 1 over x is natural log of x. You don't really need to include the plus c here. And then again, this is equal to x. So we know our integration factor is x. I'm going to return back to our differential equation. So y prime plus 1 over x, y is equal to 1 over x squared. We're going to multiply the entire thing by our integration factor, so which is x, giving us x y prime plus y is equal to 1 over x. This is our new equation that we got from the integration factor. Like I said, the premise of the integration factor is its reverse product rule, and it simplifies the left-hand side to something that's more able to be solved. This whole left-hand side becomes d dx x y prime. So it is the integration factor times y. If we want to check this out, I'm just going to do the derivative, or it's just like derivative of both. So the first derivative second plus the second y derivative first, which is 1. And this is with respect to y actually. Yeah. So then it just becomes y. So as you can see, if you take the derivative, it becomes the left-hand side. So again, this integration factor just simplifies the left-hand side. The right-hand side is not simplified. It is still just 1 over x. But this is pretty easy to take the integral of. So I'm just going to take the integral of both sides. These cancel out by fundamental theorem of calculus, giving us xy is equal to natural log of x plus c. Y is then equal to natural log of x plus c over x. Again, this has initial values. You could solve for c here, and that would give you the general form of this, but that is how we solve using the integration factor. Okay. I'm going to do we'll do this example. So this is our second order differential equation. We see that it is constant coefficients and it is homogeneous for set equal to 0. When you're looking at an equation like this, if it's just asked solve this equation, I would look at it and say what type of equation it is. How am I supposed to solve this? If that makes sense. So here, first thing we want to do is find a characteristic polynomial. So from this, y prime becomes r squared, y double prime becomes r squared, y prime becomes r, and y becomes 1. So r squared plus 2r plus 2 is equal to 0. So we're going to solve this. This is not factorable, so r is equal to -2 plus or minus the square root of 2 squared minus 4ac over 2, 1, which then is equal to -1 plus or minus I is our r, which tells us it is a complex root. I'm going to post the recording. I think all the recording for this is going to be posted to all the sections. So if you want to see this later, they should be posted later. Okay, so we see this is our r, and it is of the form a plus or minus ib, where a is equal to -1 and b is equal to 1. We know from that chart that I discussed earlier, which is going to be on your cheat sheet for this exam, it is your solution looks like this. If you're given a second order differential equation and the roots are complex, it is always of this form every time. So I would have that on a cheat sheet. Given that, I'm just going to plug these values in. So y is equal to c1, a is -1, so e to the negative t. Cosine is just, b is equal to 1, so cosine of t plus c2 e to the negative t sine of t. And that's your solution. Again, you can solve for the constants. You're given, when you have a second order differential equation, in order to solve for the initial values, to solve for the constants, you need 2 initial values. And the way you would solve this is you'd plug this value into this guy, and then you'd have to take the derivative of your solution and plug it in here, which will allow you to solve for C1 and C2. Okay. Here, let's do this one too. This is a constant coefficient, but we have a non-homogeneous term. So it is second order, it's not separable, constant coefficients, and it's non-homogeneous. How are we going to solve it? Again, characteristic polynomial comes first. Well, we see that we're going to have 2 sets of solutions. We have our complementary solution and we have our particular solution. So solving for our homogeneous solution first is the same thing that we just did. So using our characteristic polynomial, set that equal to 0. This is going to be r plus 4, r plus 1, r is equal to -4, -1. From my cheat sheet that I have theoretically, we know that the equation looks like this, where this is the first root, and this is the second root. So given this equation, y is equal to c1 e to the -4t plus c2 e to the -t. It doesn't matter the order, obviously, because it's addition, but make sure once you decide which root is associated with which constant, you stick with it. Now we need to solve for the particular solution. We know that this equation is of this is our equation. Given the way that I do this, again, is the method of undetermined coefficients. I know some students use the annihilator method, but this is just the method that I prefer. This is our f of t. Our non-homogeneous component is e to the 3t. We're going to plug in something that looks like this into our equation. So it's going to be, I call it alpha. That's just something I do. So a e to the 3t. So the method of undetermined coefficients includes an undetermined coefficient that you have to solve for by plugging it into the equation itself. So a is what we're solving for here. And then we know that our equation is going to be, our particular solution is going to be something e to the 3t. That's what we're solving for. Again, talking about not overlapping these solutions between the complementary and particular solution. This is our complementary solution right here. Since these terms don't overlap with 3t, we don't have to do anything particular, but if it did, I would multiply this term by t. So a t e to 3t. That's not happening here, so don't worry about it. But if it does happen, make sure you ensure that your particular and your homogeneous solutions do not overlap. Then taking the derivative, then the second derivative, e to the 3t. I'm going to plug this into our equation. So 9a e to the 3t plus 5 3a e to the 3t plus 4 a e to the 3t, and that's just equals to e to the 3t. Doing some algebraic manipulation, gives us 28a e to the 3t is equal to e to 3t, which tells us 28a is equal to 1. A is 1/28. Our particular solution is 1/28 e to the 3t. Finally, our equation is the sum of the complementary and particular, which is then just going to be C1 e to the negative 4t plus C2 e to the negative t plus 1/28 e to the 3t. From here, you would solve the initial value problem. So make sure you solve for the complementary and particular solution before you do any initial value problems. But this is what it would look like. And then you would solve for C1 and C2 with the method that I just mentioned. Okay. Last week 9 through 10 content I'm going to do is a Cauchy-Euler equation, just to go over how we solve these. So this is a Cauchy-Euler equation. We know because this term is a second order x squared multiplied by the second order y double prime. This is x with the y prime, and this is no x term with just y. The way we solve this, like I mentioned, is y is equal to x to the p. This is the main crux of Cauchy-Euler equations. We're going to plug this in again. Y is equal to yc plus yp. We're going to have a complementary and particular solution because it is non-homogeneous. So this is a solving for the homogeneous component. So I'm going to take the homogeneous, plug in y is equal to x to the p. So, well, given this, since we need double prime, y prime is equal to px to the p minus 1, and then y double prime is equal to p minus 1 x to the p minus 2. Those are always true. I would have this on a cheat sheet, but you can always derive it given the question. So p minus 1 x to the p minus 2 minus 3x px to the p minus 1 plus 3 x to the p equal to 0. So again, I just plugged in for y prime, and y double prime, the corresponding terms. So form this equation. I'm going to do some algebraic stuff. So x to the 2, x to the p, x to the negative 2. I separated this term. 3p x to the negative 1, separated this term, plus 3x to the p. I'm going to, these terms cancel out, the x2 and then x to the negative 2, and the x and the negative 1 cancel out, and then I'm going to pull out x to the p, giving us this, minus 3p plus 3. And this is our new, this is what we're looking for. This is a characteristic polynomial for Cauchy-Euler equations. These roots are what determine what the solution looks like. So p squared minus p minus 3p plus 3 is equal to 0. P squared minus 4p plus 3, p minus 3, p minus 1, 1, 3. These roots, again, like I put in the slides, based on the roots, that's, you know, what your solution is going to look like. I'm going to say, well, we know it's going to be of this form. Let's see, 2x p2. And then here, I know that's going to look like this. The 1, c2, x to the 3. That is the solution to the Cauchy-Euler equation. That is our complementary solution, our homogeneous solution. Now we need to solve for our particular solution, which again, we know this is what our equation looks like. This x squared y double prime minus 3x y prime plus 3y is equal to 12x to the 4th. I'm going to use the method of undetermined coefficients again, but again, you can use the annihilator method if you would like. I also want to note that for having what the solution to a Cauchy-Euler equation looks like on your cheat sheet. One of the forms is really weird. I think it's when p's are imaginary or complex, your solution looks really weird. So I would have what that looks like on your cheat sheet. I think it's like C1 e to the ax natural log of bx. It's pretty complicated, so I'd make sure that's on a cheat sheet. Okay, solving for our particular solution, I'm making my guess because of this, and we know it is going to be ax to the fourth is just going to be my guess. And a prime and a double prime. Or ax to the third. Second. We're good with this guess because it doesn't overlap with our complementary solution. Again, if this was 4 or this was 4, we would have to make this to a higher power. So I would do, if one of these were 4, I would do a x to the, it would, yes, ax to the fifth, yes. So just be 1 power higher. Okay, plugging this in for our equation. So x prime 12ax squared minus 3x 4ax cubed plus 3ax 4, 12x to the fourth. Again, doing some algebraic manipulation here. 12ax to the fourth minus 12ax to the fourth plus 3ax to the fourth is equal to 12 to the x fourth. Those cancel out. We see that 3a is equal to 12, therefore a is equal to 4, which means our particular solution is 4x to the fourth. No, sorry. Then our final solution is equal to the sum of the complementary and the particular, which is x to the, I believe it was negative, to the first, plus C2 x to the third plus 4x to the fourth. Again, from here is where you would solve the initial value problem. So you'd plug in the initial values and solve for C1 and C2. If it's non-homogeneous, make sure you do it after you solve for the YP. It is not correct if you don't solve for the YP beforehand. But okay, that is all I want to cover for weeks 9 through 10. Again, all of these solutions to all of these questions are linked in my week 9 slides. So if you have any questions about that, that is a good resource, as well as a link to, me solving them a couple weeks ago. While we're on the topic of, this is a side note that I would like to make. Okay, this is quiz 5 from 3-4 weeks ago, a little bit ago, March 31st. So yeah, 4 weeks ago. I just wanted to emphasize, because I didn't really do any questions with the Wronskian, but I wanted to talk about it real quick. So the premise of this question, I know a lot of people struggled with it, was they wanted you to take x squared, sine of x and cosine of x, and put that into the Wronskian. So it'd be a 3x3 Wronskian with those terms in the top, their derivatives in the first row, and then their second derivatives in the third row. Then they wanted you to determine if it's 0 or non-zero. This question was particularly tricky because of the trig functions, and the professor has included like trig identities that not necessarily everyone would have known, so it was a little bit trickier, but the premise is still true that if it's non-zero, so if the Wronskian was not equal to 0, we know that the functions are linearly independent, which I think a lot of people understood. But the thing that I think a lot of people lost grasp on was, what does linear independence mean? So this equation is, does there exist non-zero constants, so C1, C2, C3 that are non-zero, such that this equation holds true? They end up being linearly independent. The Wronskian was non-zero, linearly independent. That means these constants, the only solution to this equation here, this C1, C2, C3, is the trivial solution when all of them are equal to 0, right? So since they're linearly independent, you cannot make them from each other. It is impossible. That is the definition of linear independence, is you can't make the solutions, you can't make the equations from each other. So that's just an idea that I wanted to mention, that linear independence implies that you can't linearly combine them to get each other. Therefore, if the Wronskian is non-zero, these constants don't exist and the only solution is the trivial solution. But that's just a side note. Okay. Back to these slides. Sorry. Okay. Okay. All right, working on week 11 content. So this question is, find the general and specific solutions of this equation here. So I'm just going to rewrite it on here real quick so I can do it on my iPad. And also the next question. Okay. So this question, week 11, it is a x prime equals a x, which is what we have here. We want to solve for the eigenvalues and the eigenvectors, and that allows us to form the solution set. So first thing we're going to do is solve for the eigenvalues. So a minus lambda I. And then we're going to find the determinant of this, which is just equal to lambda squared plus 1 is equal to 0. We want to solve for our eigenvalues, which is just the roots of this equation. So here we see that it is 0 plus or minus I. We have complex eigenvalues. When we have complex eigenvalues, the way we solve this is, like I mentioned, the general solution looks like the generalized eigenvector. Ooh, that was bad. E to the eigenvalue t times cosine of, oh, sorry, at cosine of b of t plus I sine of b of t, where that is our eigenvalue. Here we have a complex eigenvalue. Our solution, we need to find our eigenvector associated with this. So when we have complex solutions, technically we have two solutions. We have when we add them together and when we subtract, right? So technically this is negative I and positive I. For these, you only need to choose one of them. I think by convention, it's usually the positive eigenvalue. So just I here. So like if it was like 3 plus or minus 4i, you could do 3 plus 4i. And then we solve for the eigenvalue with that we solve for the eigenvector with that eigenvalue. So here, we're going to choose lambda is equal to I. And to solve for that eigenvector, I'm going to plug it back into our equation, or not equation, our matrix. And then solve for the kernel here. This can just be here. We see that from here, negative I x1 plus x2 is equal to 0. So x2 is equal to I x1, which can be represented in the eigenvector as this form. So this is our generalized eigenvector for this system. Now we can revisit what our solution should look like. X is here, e to the, we see a for this term is 0, so 0t. Cosine of 1, because coefficient of I here is 1, so I'm just going to not include it. T plus I sine of t. So that is our solution. This is what our solution is going to look like. We just have to redistribute a bit to get it to the real solutions. As we can see, there is an imaginary component, but we want to make sure that we get it with all of them, with it all being real. This involves distributing, or I guess it's the other way around, distributing this term into the vector. So cosine of t, I sine of t, and then here, I cosine of t plus I squared is -1, negative sine of t. Redistribute these a bit so that the ones with the imaginary terms go with the imaginary terms. So we actually pull a constant out, and then cosine of t negative sine of t plus c2 sine of t cosine of t, where these are these values, these functions, and these are these functions. So we took the real components, grouped them together, and put them into a column vector. We took the imaginary equations, grouped them together, put them in a column vector, and then we just added constants. And then this is our solution. Perfect. So this is what the solutions to an imaginary complex eigenvalues for a diagonalizable system look like. The other question, this is similar, but it is going, spoiler, it's going to have real solutions, real eigenvalues. So I'm going to turn this into a x prime equals ax system just by plugging them into the matrix. And again, it's going to look like this. Very straightforward. Oh yeah, so for this one, again, we have initial values. If I was given, for this, you would take, I'll just like do it out here. So we have x of 0 is 6, y of 0 is 3. We need to solve for c1 and c2. So x is equal to c1 cosine of t plus c2 sine of t. And then I'm just getting these from this matrix up here. We would plug this in here and this in here. So 6 is equal to c1 cosine of 0 plus c2 sine of 0 plus 3 c1 negative c1 sine of 0 plus c2 cosine of 0, which tells us this goes to 0, this goes to 0, c1 is equal to 6, and c2 is equal to 3. This is a pretty straightforward initial value problem, and then your solution would just be plugging these in. Cosine t. So that's how you would do it for a system sometimes not that easy, but that's the premise behind it. Okay, back to this guy. We need to solve for the eigenvalues. We're going to do that as we've been doing it. 2 minus lambda, -3, -3, 10 minus lambda. Sorry. Okay. Then we've got 2 this, 10 minus this, minus 9, which is equal to here, this. Sorry, I'm just saving a little bit of time by showing what it's supposed to become. All right, our eigenvalues are 11 and 1. I didn't go through that because solving for eigenvalues is pretty rudimentary at this point. I'm going to solve for the eigenvectors, which end up being 1, -3, and then 3, 1. And our solution set is going to be, it's always of this form, T V1 plus C2 e to the T V2. So here, just looks like this. C1 e to the 11T 1 -3 plus C2 e to the T 3 1. And that's our solution. Again, initial values, you can plug in the initial values to solve for the constants, but I just went over that. So if you want to do that on your own, you can. But that is complex and real solutions to diagonalizable systems. Let me see. Sorry. Okay. Last week 11 question I want to go over is converting to an equivalent first order system. It looks like, sorry, 1 second. Okay, this is we have multiple differential equations, second order differential equations, and then we need to turn this into equivalent first order system. So this is the system that we were given. And we need to convert it to a first order system. So we have two differential equations, they're second order, and we want to make it all into one big system. Here, this is going to be a 4x4 system. So basically, we want to look at this equation and then this equation here. So, sorry, let me write these separately. The crux here is that I'm going to set x1 equal to x, and then x2 equal to x prime. We only need two terms in order to span this whole differential equation here. But this, because then as we can see, x2 prime is equal to x double prime, which is here. But this is the main idea. This was on one of the quizzes, and on the rubric, it was like, can they make this relationship? So making sure that you understand, in order to convert it to a first order system, you need to make this true. But yeah, so here we have this, and then also we have x3 is equal to y, and x4 is equal to y prime. So again, the x1, x2, x3, x4, those don't mean x, so don't box yourself into x's mean x's, because we're asserting it equal to a y here. It's just the way that this works. So this system is going to have four terms, so it's going to be x1 prime, x2 prime, x3 prime, x4 prime. This is our entire system. And we're going to have x1, x2, x3, x4. Looking at this differential equation, this x double prime, I'm going to turn this into something in terms of these variables. So again, x2 prime is equal to x double prime based on virtue of this. So this equation is x2 prime equal to x1 and then x3. This is the exact same. It is equivalent to this based on the variables that we established and the relationships that we established. So then here for the y double prime, we're going to do the same exact thing. So x4 prime is equal to this. So 2x1 minus 3x3. These are equivalent. In order to make this true and not just arbitrarily deciding them, we need to establish these relationships within this matrix. So the two main important relationships is that x1 prime, okay, sorry, let me get this up a bit. Here, I'm just looking at each row. What is x1 prime equal to? What is x2 prime equal to? What is x3 prime equal to? And what is x4 prime equal to? x1 prime, in order to figure out what that is, I'm just going to differentiate both sides. This x prime is equal to x2. That makes sense. I combined these two equations essentially. So x1 prime is equal to x2. That is the only thing it is equal to. x2 prime is equal to this equation here. You're given it. That is part of the problem. So it is equal to 1, 0, 1, 0. Same thing for x3 prime. So hello. x3 prime is equal to y prime, which is equal to x4. I'm going to plug that in like that. Same thing I did for x1 prime. And then x4 prime is equal to this equation, which I can just insert 2, 0, negative 3, 0. This is our equivalent first order system. That is how you would do it for two second order differential equations. They might ask this, I think, because it hasn't really been tested. They only did one second order differential equation, making it to a first order system. It hasn't been two differential equations or like three, because you could do this for up to like x double prime, y double prime, z double prime, w double prime. There's many different things that it could be. So I would be prepared for a question like this on exam. How did I got rows 1 and 3? Yeah, absolutely. So row 1 is just here. Oh, rows 1 and 3. So row 1 is equal to, oh, sorry, that is wrong. Row 1 is this relationship here, this guy. So in order to make this a true system, x1 prime is equal, we know that x1 is equal to x. I differentiated both sides. I put prime, prime, and I know that x prime is equal to x2. So therefore, x1 prime is equal to x prime is equal to x2. That is what is in row 1. Same thing for row 3. We see that we need to know what x3 prime is equal to. So I'm going to take my x3 prime term, differentiate it. So we get x3 prime, which means it's y prime. And I know that y prime is equal to x to the 4th. So all I have is that x3 prime is equal to x to the 4th, x4. Okay, awesome. So this is all of week 11 content that I'm going to go. That is really all of week 11 content. Okay. We are back to the slide deck. Oh, this is actually, sorry, this is another week 11 content question. I'm not going to do it just because this is a work, these are all recitation questions. The recitation solutions are in that link that I sent. This is the exact same thing that we did, except I guess it's a little bit different. So it's just saying we have the form. Actually, I'll discuss this one. Why is one? Write it down real quick. Sorry. Okay, we'll do it here. Okay. Okay. This is our question that we were discussing. Right. Let A denote the 3 by 3 matrix. Find the eigenvectors and eigenvalues of A. Pretty straightforward. A minus lambda I is 1 minus I, 0, 0, 0. Oh. A is 1, 0, 0, 0, 1, 2, 0, 2, 1. So given A, I'm just going to solve for its eigenvalues, which is what we've been doing this entire year, which is equal to negative is positive. This is skipping a few steps. 1, negative 1, 3. Skipping a few steps again. The associated eigenvectors, I'm not going to go through because it's pretty straightforward because it's diagonalizable. 0, negative 1, 1. And then 0, 1, 1. These are eigenvalues and our eigenvectors. Part B is find the diagonal form D of A is equal to P D P to the negative 1. We know that D is our eigenvalues along the diagonal. So 1, negative 1, 3. And the associated P matrix is the corresponding eigenvectors in the corresponding rows. So here, 1, 1. Now it wants us to compute e to the dt. E to the dt is just this e to those powers. So e to the dt is e to the 1t, e to the negative 1t, e to the negative 3t. Pretty straightforward. However, the last part of a question is using a e to the t, e a to the t, p e d to the dt, p inverse, write the general solution for the system. So this is kind of exploring another way to get the general solution to these equations, these systems. So this is a true assertion. Usually it's d p inverse ap. This is our normal equation for diagonalizing. As we can see, p and p inverse have flipped when we did, instead of we're raising it to the exponential. This is just true. They might ask, solve for it this way. So I'd be familiar with that fact that is true, but it's just this. So e to the at is our solution, and it's equal to our p, negative 1, 1, 0, 1, 1. Our e to the dt, et, nope, e to the negative t, e to the 3t, and then our p inverse. Going to do this, which after some matrix multiplication, we can distribute this and we get a matrix, which we can then show that it is actually equal to what we expect it to be, which is just the associated eigenvectors and their eigenvalues of this form. So the main purpose I did this question is just because this is related to fundamental solution matrices, and this equation is this equation is something I would have on a cheat sheet just in case something's asked about it. Okay. Back to slide deck again. Okay, so we did this question. Now we're into week 12. Okay. I am just going to, I have solutions to this, and I'm just going to talk through them to save a little bit of time. So we're doing find the particular solution to, so we're given a non-homogeneous solution, a non-homogeneous system. There is an F term in this case. For systems differential equations, that F is going to be a matrix rather than just a function. And we want to find the solution to this. So how are we going to solve this? And then also the next question is finding the fundamental solutions matrix to this system, which is also non-diagonalizable. So I'm just going to walk through both of these. Again, this is on that sheet, that document. This is week 12. So let's go over this. So we're given this system, and we see that it is non-diagonalizable. This A is non-diagonalizable. We know this because it is of the Jordan form right here. It's pretty obvious that it's non-diagonalizable. So our eigenvalue is lambda equals 2 with an algebraic multiplicity of 2. We're going to solve for the Jordan canonical form as normal, so that we're solving for our P, which again includes solving for the eigenvector in the kernel of a minus 2i, and then for in the kernel of a minus 2i squared. Blah, blah, blah. So this is all Jordan canonical form stuff, not necessarily related to differential equations, which I think will be gone over tomorrow in the linear algebra portion. But again, pretty straightforward Jordan canonical form solutions here. From here, we find P is equal to 0, 1, 1, 0, and our Jordan form, our J, is equal to 2, 0, 1, 2. This is the crux of non-diagonalizable systems of differential equations. So here, we need to solve for y, and then we use y to solve for x. Our solution to this equation is x. It is x prime equals ax. But we can't directly solve for that because it's non-diagonalizable. In order to do that, we solve for y. Y is a set of solutions that is specific to Jordan form. It is derived in a later question on this recitation if you want to look at it, but it's of the general form. Like this is the general form, so let me just write this out. For 2y3 for a 3 term 1, who's going to. This was on the quiz, and I think a lot of people got this wrong. So let's just discuss it real quick. It looks like, so let's say y1 is this first eigenvalue with algebraic multiplicity of 2. So it looks like this, and then we need 2 terms for it because it has algebraic multiplicity of 2. So it's the same here. And then this is T10. And then also if we have 2, which is simplicity of 1, C3 each here. These are distinct. Okay, so this kind of summarizes a little bit of, this would be a 3x3 matrix that's non-diagonalizable with one eigenvalue with algebraic multiplicity 2 and another eigenvalue with algebraic multiplicity of 1. This is what the form is going to look like. These eigenvectors in this y term have this form where it goes 1, 0, 0, and with however terms you need, then it goes T10, then it goes T squared over 2, T1, and so on and so forth on that power. So it'd be t3. This is actually exponential, so this would be 6 t squared over 2, and then t, and then so on and so forth. This is our y. It is always of this form, and it's dependent on the specific matrix and the eigenvalues, how you determine it, but that's the general form of y. So this is our y right here. But again, we're solving for x, not y. X is equal to p times y. As we can see from this y, we didn't use our p. We didn't use our eigenvalues that we determined, our eigenvectors, right? We only use our eigenvalues. X equals py is where we use the specific Jordan form of this solution. Because as of y, we use our general eigenvectors that are all these general vectors that are associated with this, and then our eigenvalues. This is where they actually get introduced. So you take y and you multiply it by p. So this gets multiplied by p and this gets multiplied by p. From there, then you have x. Now we have our x, what we need. And this is what it looks like. This one's pretty straightforward, it's pretty simple, but that's the idea. For non-diagonalizable systems, you have to solve for the Jordan form. You form that y solution, and then you find x. X is, you have to make sure you end up solving for x. Y is not your solution. Make sure you find x. The fundamental solutions matrix is what I was talking about earlier, where it is the matrix such that when you plug in 0, it forms the identity that is of the solutions. So here, if I plug in, so I reordered the equations, the solutions, switching them, but it's addition. And then if I plug in 0 here, I'm going to get 1, 0, 0, 1. 1, 0, 0. Yeah, exactly. So this is the fundamental solutions matrix based on the solution. Okay. Now going over a x prime equal to ax plus f. So example. So we're given this equation. We need to solve for the general solution because we know that the general solution is the sum of the homogeneous and particular solutions. This theme stays. It never goes away. With systems, with not systems, it's always that you need to add the homogeneous with the particular to get the general solution. Here we solved for the complementary solution. We found the eigenvalues, found the eigenvectors associated with them, given this complementary solution here. Boom, great. Particular solution. I'm looking at my complementary solution. I see there's an e to the 4 term and an e to the 2t term. I look at our f term and I see that there is no overlap, right? Because we have e to the t terms. Because there is no overlap, we can use method of undetermined coefficients. If there was overlap, we would need to use variation of parameters, which I'll discuss later in a minute. So solving for the particular solution using method of undetermined coefficients, I'm going to run through this real quickly because I am running out of time. But this is supposed to be 6. You make a guess like we were doing earlier, our undetermined coefficients. This time the undetermined coefficient is just a vector. It's not just a value. So it's this a, which is a is a 2x1 vector. Or 2x1 column vector. So we take it and we do exactly what we were doing earlier. It's just a little bit more complicated because we have matrices involved. We find the first derivative of it, we plug it in to the equation that we are given. This goes into here. Luckily, the e's to the t's cancel out, which is great for us. So we're going to cancel those e's to the t's out. And then it's just a bunch of algebraic manipulation here. This is something I put on a cheat sheet because it is kind of the same for all of these method of undetermined coefficients, and it's kind of weird math, complicated a little bit, but it's true. So I would just hold that. So basically the whole thing here is we're solving for this vector, which involves a lot of moving stuff around, blah, 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 matrix multiplication. Ultimately, A is equal to 6, 6, 12. That is our column vector. That is our particular solution. As we know, our general solution is the sum of the homogeneous and particular solution. I've said that about 20 times today, just trying to emphasize as much as possible. So this is our complementary solution, and this is our particular solution. So we got particular from method of undetermined coefficients because we were able to use it since the guess and the homogeneous solutions didn't overlap. Okay. Let me see if there's any other week 12 stuff I want to go over. This is the derivation of those y vectors that we were talking about. This is the same thing that we were doing. Yeah, just a solution with 3 terms. And then here, this discusses how the f really does determine what method you use. So here the f is e to the 2t, which doesn't overlap with the complementary solution. So we use method of undetermined coefficients. However, if it does overlap here, so we have e to the t, since they overlap, we're going to use variation of parameters. And variation of parameters is this equation here. This solves for the particular solution to an equation. You just need x, which is equal to this. It's just equal to dp the inverse, e to the, remember how this is equal to this. We need x, which is equal to e to the at, which is this. It's also the fundamental solutions matrix. Then you use this x, plug it in, and do a lot of calculus, lots of integrating. But that gets you your yxp, which here is this matrix right here, which we just add. So this is xc, and this is xp. Okay, that is all of mostly week 12. I would do some practice with these, especially because they're trickier and require a little bit more algebraic manipulations. Okay, last week, week 13, we have 7 minutes left. Okay. Okay. We just went over both of these questions. Okay. Week 13, again, is pretty straightforward. It is just those face portraits and what does the system look like. So looking at the makeup quiz, I guess. So this is kind of what I'm expecting them to ask. They've asked a lot about week 13 on these quizzes, week 6 and the makeup quiz. So I don't know how heavily they're going to test on it on the exam. I feel like they've already tested pretty sufficiently and completely on it, but they could, again, still ask more. I'm just looking at, this is the makeup quiz. So given the nonlinear autonomous system, these two, determine which figure represents the trajectories. So this is a slightly different question than they asked in week 6. But we look at this, we need to determine the critical points. And from the critical points, using the Jacobian, what does it look like? So at the critical point is where that node, that saddle point, everything is going to happen. So it is at, that's like the coordinate for it. So here, y of 1 and y of 0 is going to be a critical point, and plugging that in. So y of 1 and y of 0. Sorry, I haven't looked at this, but I just wanted to discuss like the idea behind it. And from there, one second. Okay, here, so y of 0, that means x equals 0 or 2. Y of 1, x equals 0, x equals 1. So we have 4 critical points. Actually, I'll just show the professor's solution to this. So I think it's pretty helpful. We have this system. We found the critical points by making both of them equal to 0, finding these 4 critical points. The Jacobian is the partial derivatives of the first. So here it's the partial derivative of this with respect to y, then, but this is respect to x. Yes, so respect to x, respect to y, respect to x, respect to y. This is this x prime one, and this is this y prime one. From the Jacobian, you plug in each critical point into the Jacobian matrix. You see what does this do. So here we see it's a source because they're both positive and not equal to each other. We see this is a saddle because this diagonalized gives us a positive eigenvalue and a negative eigenvalue. This again is a saddle because positive and negative. And this is a sink because they, I believe, let me see. It is a sink node because they're both positive, but not equal. Or they could be equal to each other. Yeah, they're equal to each other. Yes. So that is, I guess, the main idea behind these week 13. And then I'm just going to go over this real quick. The last 3 minutes. Okay, so this is week 13. This is something that I think would be useful to have on a cheat sheet, which is just the diagram of how the types of critical points change based on the eigenvalues. And so we see we're graphing the determinant versus the trace, which is kind of interesting, but that kind of tells you more about the system. So this is a system. We find the eigenvalues. We see they're both positive and not equal to each other. That gives an unstable or improper source node. We have our eigenvalue, our eigenvectors. The source is going to come from along the eigenvectors. And I believe we are going along the, so as you can see, these y trajectories, these yellow trajectories go along the greater eigenvalue eigenvectors. So it's going along 1, 1 instead of negative 1, 1. And that is what our phase portrait looks like. Same thing for this system. It's imaginary this time. So we want to see what does that look like. I would just have what I was talking about earlier in the slides based on what is the eigenvector, what is the phase portrait, what is the eigenvector, what is the phase portrait. It's a spiral. This is our eigenvalue. It's outwards because both of these are positive. Like this A term, like A and then B, because they're both positive. Because A is positive, I believe. Because A is positive, it goes pointing outwards, and because B is positive, it is going to be spiraling to the right. Yes. Okay, last, again, this is what we just talked about. You find the critical points by setting both x prime and y prime equal to 0. Finding the Jacobian is just the partial derivative with respect to x, with respect to y, respect to x, respect to y. You find the Jacobian, and based on what the Jacobian matrix for each critical point looks like, you can determine stable mode, unstable mode, saddle point. What does that look like? You should have in your mind what that should look like. This was just like the application of it. So the trajectories looked like, and yeah, okay. Yeah, so for the week 13, again, I have this in my week 13 slides. 13, yeah, I think so. Okay, yes. So based on the eigenvectors, what does it look like? And again, these are the eigenvectors of the Jacobian. And then same thing for imaginary or complex. As you can see, based on the eigenvalues, what is the geometry with the Jacobian? But yeah, that's about all of the content that I wanted to go over for differential equations for this exam. I hope this was useful, and I wanted to wish everyone good luck studying for everything for the exam on Thursday.
Thanks, Ryan. Oh, wait, sorry, I just totally forgot one question. Really quick. On the week 12 recitation solutions, for some reason, the link isn't working to open them.
Oh,
Sorry
okay.
if you attach a link.
Yeah, I can try to fix that.
Thank you so much. Have a great night.
Thanks, you too.
Thank you.
Thanks, Ryan.
Of course.